So, one last thing to catch up on is we talked about the beautiful planetary nebula the sun will make, but then what about that core? I want to look a little more closely at that white dwarf, which is, in some sense, the end result of what the sun will be. And white dwarfs have an interesting discovery history. Shortly after measuring the first successful parallax measurement, Bessel followed another star, which he thought would be likely Sirius, which we know is very nearby. And as he measured its proper motion, he noticed that Sirius wobbles, and he immediately understood what was going on. He knew about Newtonian physics. Sirius has a binary partner. The search for what was called the pup was on. People wanted to find it. It turned out to be a very challenging prospect, but in 1846, indeed, the star was found, and the reason it had been so difficult to detect was because it was so much dimmer than Sirius. Sirius has a luminosity of 23 solar luminosities, and Sirius B, its partner, only 0.03 solar luminosities. Clark was very fortunate. The year that he was making the measurement turned out to be a year of Astron, which is aphelion for a binary system. It's the time when, in their elliptical orbits, Sirius A and B were farthest apart. Their period is a little over 50 years, and this will play into the history in a minute. Measuring their orbits, we can figure out their masses. We're good at that by now after the experience of the previous week. And Sirius, as we mentioned, has a mass a little over 2 solar masses, and its partner has about a mass of 1 solar mass. So it's a dim star with 1 solar mass. It's certainly not a main sequence star. We know that because a main sequence star with 1 solar mass would have about 30 times that luminosity. Okay, well, the game was on to find the spectrum of these objects. You needed to measure them again, you needed to wait for Apastron to come around, and it did in 1915, and an American astronomer named Adams managed to measure the temperature of the 2 stars, and his results shocked the world, because the temperature of Sirius had been known. It's the 9,900 degrees Kelvin that we knew, but the temperature of the partner turned out to be not a lot less, as you would expect from the low luminosity, but in fact a lot more. Hooky? So, now, if you know the temperature and you know the luminosity, bada beam, sigma t to the 4th, we can compute the radius of Sirius B, and the radius of Sirius B turns out to be less than 1% of the solar radius, more impressively, less than Earth's radius by slightly. The radius is less than Earth's radius. This is an object with the size of Earth and the mass of the Sun. This is extraordinarily dense. The surface gravity on Sirius B, you just compute, plug the mass you know, divided by the radius squared, scale to Earth, and you find that the surface gravity on Sirius B is only 450,000 times the surface gravity on Earth. You do not really want to go there. And astronomers in the early 20th century scoffed. They figured there's got to be a mistake. There's no way that such an object could exist, but it was there, so it was there to be studied. Its spectrum showed very broad hydrogen absorption lines. Well, if you have an atmosphere of hydrogen in this kind of gravitational field, it'll certainly be very compressed, and you expect very broad absorption lines, but otherwise it was just a featureless black-body continuum. You can make estimates of given the mass and the radius of the central density and pressure, and the central pressure is millions of times more than in the center of the Sun. The central temperature is 70 million Kelvin. Well, that tells me something. If we know that there are hydrogen absorption lines, we know the universe is made of hydrogen, but there better not be that much hydrogen in this object, because if there was, it would fuse, and then the luminosity at these temperatures would be way, way higher than this 3/100ths of a solar luminosity. So this is a hydrogen-free object, something rare. It was poorly understood, but now we know. The way to make a hydrogen-free object is first condense the heavy byproducts of helium fusion into the core of a star. You get basically an object that is almost exclusively carbon and oxygen. Blow away the hydrogen envelope, and what you're left with will be a white dwarf. So now we know. White dwarfs are the degenerate cores of stars whose mass is not too high. Turns out that You can have a mass as high as 8 solar masses. We'll talk about what happens to more massive stars in a few clips. Their composition is indeed hydrogen-free. They're almost exclusively carbon and oxygen. Their masses, after we measured many of them, lie in this narrow range between 0.4 and 0.7 solar masses for the most part. Given the much larger range of stellar initial masses, this gives you a sense of the mass loss that a star undergoes in the course of its last thermal pulsing days when it leaves an exposed mass. And here comes this guy Chandrasekhar again with another interesting discussion. And this time, I want us to follow through with this. So let's understand what it is that Chandrasekhar tells us about the weird behavior of degenerate matter. So what Chandrasekhar says is this. So consider an object here which is completely degenerate and not luminous, so we can imagine that it's isothermal, but temperature will play no role. And we'll give it a radius r and a mass m. So what do we know about this object? Well, we can figure out its density. We could imagine, for the sake of argument, that the density is uniform, although it's not going to be. And so if the density were uniform, then the density would be m divided by 4 pi over 3 r cubed. Now, that's not true because the density is not uniform, but I want to compute some kind of characteristic density. So I'm going to say that it's going to be some number, which I shall call a, say, times m divided by r cubed. A will incorporate 4s and pi's and the relative geometry of the situation in 2/5 and whatever else, some number of order 1 times m over r cubed. What this tells me is that if this object is held up by electron degeneracy pressure, then that pressure, Pe, is given by K for electrons times rho to the 5/3. And I plug this expression into this, and I get a new constant, 8 to the 5/3 times K, which I might as well call C. And then I get m over r cubed raised to the 5/3 power. So the electron degeneracy pressure is dependent on mass and radius in this form. That's m to the 5/3 divided by r to the 5th. If you write it out explicitly, that's worth writing out cleanly. Let me write it out cleanly. So for some number c, the electron degeneracy pressure is given by this. Now, what is the statement? The statement is that this object is supposed to hold itself up against gravity. That means, let me draw my object again since I erased it, at the edge of the object, pressure is 0. It's touching space. And so I can ask, how much pressure do you have to have in the center in order for for that to be enough to hold the object up? In other words, what is the gravitational pressure? And just dimensional analysis tells us about how to figure out the effective contribution to pressure by gravity, because, well, of course it'll depend on g, right? And we can make an acceleration out of g and m and r, which are the only parameters we have, by taking g m over r squared. And we can turn that into a force by multiplying by the only other thing we have, which is m. So gm squared over r squared is a characteristic force of gravity. We want a pressure, so that needs to be divided by area. So I multiply by the only relevant thing that can be an area. And this is completely wrong. This is not the pressure due to gravity. But if I put some number here, which I'll call c prime, then it is. And exactly what depends where exactly you're measuring the gravitational pressure due to gravity and what exactly the distribution of mass is in, so on. But some version, c prime times g m squared over r to the 4th is always a good estimate for the gravitational pressure, or if you want, the difference in pressure from here to here, which is the amount basically by which the pressure in the center has to be higher than the pressure at the edge in order to hold the thing up. So let's take note of this gravitational pressure calculation that we did. I just copied it and wrote it out cleanly. And now Chandrasekhar notes, set one equal to the other for the case of an object that's held up by degenerate matter. And what do? We set this equal to that, and I find that c prime times g times m squared over r to the 4th is equal to c times n to the 5/3 divided by r cubed to the 5/3 is just r to the 5th. Okay, so I get some cancellations. I have all kinds of constants I don't know what to do with. But these r's go away, and 4 of those r's go away. And 5/3 is less than 2 by 1/3, so I can get rid of this and raise m to the 1/3. So multiplying by r here, I find that m to the 1/3 times r, and then dividing by these constants, is some number, c over c prime g. And then it's easier to take the cube of all of this, which is mr cubed is this whole constant, some number cubed. Notice that this constant depends a little bit on the geometry, but it doesn't change too much. Well, that's very reasonable. The mass of an object times the cube of its radius, essentially times its volume, is a constant. That is the weirdest thing ever. Let's write that out and think what that means. That means that if you have two white dwarfs and one is more massive, the one with the bigger m has a smaller radius. Degenerate matter works in a very, very weird way. The more massive a white dwarf is, the more it has to compress in order to hold itself up against gravity, and therefore the smaller it is. This already hints at something very bizarre. As you make the white dwarf more and more massive and it becomes smaller and smaller, the electrons are pushed to higher and higher energy levels, and eventually relativity comes into this. That's next week's stuff. But when you make the correction for relativity, you find that eventually, if you make the mass too big, the radius becomes 0. A white dwarf cannot exist with a mass bigger than what is called the Chandrasekhar limit, and the Chandrasekhar limit is about 1.44 solar masses. You cannot have a white dwarf with mass bigger than that. A degenerate object held up by electron degeneracy cannot have a mass bigger than that. Our observations are consistent with this. Here is the weird mass-radius relationship for white dwarfs, for degenerate matter. What we computed is the non-relativistic blue curve. You notice that the larger the mass, the smaller the radius. Now that's pretty weird. The relativistic corrections become important at large masses and small radii, and they show you that at the Chandrasekhar limit, that's the end, you cannot pack more than 1.44 solar masses into a chunk of degenerate matter. Something bad will happen. What will happen? We'll see soon.